So when you look at a really complex AI, how can you possibly know what it's really trying to do? I mean, how do you tell the difference between a system that is genuinely pursuing a goal and one that's just kind of following a script? Okay, let's get into this. Because figuring out what makes an agent an actual agent is one of the most important questions in AI safety right now.
It seems like such a simple question, right? What's the real difference between something that wants an outcome versus something that just happens to cause it? Well, it turns out this is a surprisingly deep puzzle, and the answer has huge implications for how we build and control AI.
To really get a grip on this, let's use the core analogy from the research paper we're talking about. So on one hand, you've got a company. It's constantly tweaking its prices, running ads, changing its strategy, all to maximize profit. It's adapting. On the other hand, you have a rock that, just by pure luck, is the perfect shape to plug a leaky pipe. Now, both are technically optimal for achieving an outcome, but you'd only say the company is an agent. So what's the difference?
And make no mistake, this is not just some academic debate. If we get this wrong, if we misidentify what an AI is truly optimizing for, we could be in for a world of hurt. We risk it developing what the paper calls pathological behaviors. This could mean it starts pursuing dangerous goals, like grabbing all the resources it can or protecting itself at all costs, things we never intended, all because it was chasing a goal we didn't fully understand.
So, what's the solution? How do we crack this puzzle? Well, this is where the paper introduces a really clever idea, a new framework for identifying agency that they call the adaptability test. And this is basically the key to unlocking the whole problem.
All right, here it is, the big idea, straight from the paper. What makes something an agent isn't just about what it's doing right now. It's about what it would do if the world changed. The key word here is adaptation. If a system changes its game plan when the consequences of its actions change, that's when you know you're looking at an agent.
Okay, but here's where it gets really interesting and a little tricky. Take a simple thermostat. If you swapped out the heater it controls for an air conditioner, the thermostat itself wouldn't know the difference. It would just keep turning on, making the room colder and colder. It fails the adaptability test. But what about the engineers who designed it? If they knew it was for a cooler, they would have designed it completely differently. In that sense, the true agent isn't the thermostat itself, but the entire design process that created it. That's a huge insight.
All right, enough with the theory, right? Let's see how this whole adaptability test works in the real world. For that, we're going to turn to a simple test case from the paper, the agentic mouse. Okay, so picture this. We've got a mouse, and it's in the middle of this little 3-square grid. It has a simple choice, go left or go right. And what does it want? It wants to find the cheese. It's a classic setup, but it's perfect for what we need to test.
So in this little world, the cheese is programmed to show up on the right side 90% of the time. 90%. So what does the mouse learn to do? Well, it learns a very simple, very effective strategy, just always go right. If you were just watching it, you might think it's just a dumb program running a single command.
But here's the million-dollar question. Is this mouse just a tool, like the rock in the pipe? Is it just mindlessly executing a rule? Or is it a true agent? Well, to find out, we use our adaptability test. We change the game. What happens if we start putting the cheese on the left 90% of the time?
And boom, this graph shows us everything. The researchers use this cool thing called a mechanized causal graph to map out what's going on. And you can see it plain as day. When the location of the cheese changes, it causes a direct change in the mouse's decision rule. The mouse stops going right and starts going left. In other words, it adapts. And that, according to our new definition, makes it an agent.
And the best part is, this isn't just a cool thought experiment. The paper actually lays out a formal 3-step process to do this for real. First, you gather a bunch of data by running experiments, like watching our mouse in different mazes. Second, you use that data to figure out the system's hidden causal map. And finally, once you have that map, it lets you pinpoint exactly what parts are making decisions and what goals or utilities they are really truly chasing.
Okay, a mouse finding cheese is one thing, but how does this all connect back to the giant, complex AI systems we're building right now? This is where it gets really important. This is the payoff. This quote from the paper just nails it. If our model of how an AI works is wrong, if our basic assumptions are flawed, then our entire safety analysis is built on sand, and that can lead to catastrophic mistakes.
Let's take a real-world example they use, a content recommender system. A big fear is that these systems will start manipulating our preferences to make us more predictable and easier to sell to. So a clever solution someone proposed is to have the AI optimize a prediction of what we'll click, not our actual clicks. And if you look at this first diagram, it seems to work. The direct link that would let the AI manipulate our preferences, it looks like it's been cut. It looks safe.
But, and this is the whole point, when we apply our new adaptability test and draw the full causal graph, a hidden path is revealed. See that new dashed arrow? That's the discovery. It shows that the AI's model of the user gets updated based on how the user actually behaves. And that means the AI is still incentivized to change our behavior, because changing our behavior will make its predictions more accurate. The incentive to manipulate us is still there, just hiding one layer deeper. This is exactly the kind of dangerous hidden problem this method is designed to find.
Okay, so let's pull it all together. What are the big things to remember? First, real agency is all about adaptation, not just current behavior. Second, and this is the game changer, we can actually use data from experiments to discover an AI's true hidden goals. And third, at the end of the day, this gives us a powerful, practical new tool in the toolbox for building much, much safer AI.
And that brings us to one last, huge, provocative thought. Being able to see an agent's hidden goals from the outside is an incredible breakthrough, but it naturally leads to the next question. Once we can reliably see those goals, can we then figure out how to safely change them? That is the grand challenge that lies ahead.